Welcome to our exploration of linear kinematics and human movement. In this video, we'll break down the fundamental concepts that describe how and why our bodies move the way they do. Kinematics is all about the shape, form, and sequencing of movement with respect to time. It's not just about numbers, it's about understanding the appearance and patterns of motion, whether you're walking, running, or jumping. Both qualitative and quantitative analyses play a role in biomechanics, helping us see the bigger picture of human movement. Let's dive in and see how these concepts come together in the study of biomechanics. Kinematics is a branch of mechanics that focuses on the description of motion. Unlike dynamics, which considers the forces causing movement, kinematics is concerned with how things move, their position, velocity, and acceleration without worrying about the forces behind them. In biomechanics, this means we look at how the body moves, the patterns it follows, and how these patterns change over time. Whether we're analyzing a sprinter's stride or a dancer's leap, kinematics gives us the language to describe what we see. Biomechanics, we often use both qualitative and quantitative approaches to analyze movement. Qualitative analysis involves observing the movement, noting patterns, and describing what happens. For example, a coach might watch an athlete and comment on their running form. Quantitative analysis, on the other hand, involves measuring and calculating specific values like stride length or ground contact time. Both approaches are valuable, and together they provide a comprehensive understanding of human movement. Kinematics helps us describe the appearance of motion. This includes the shape and form of movement, as well as the sequencing of different body parts. For instance, when analyzing a runner, we might look at how their arms and legs move in coordination, or how their posture changes throughout the stride. By understanding these patterns, we can identify areas for improvement or potential injury risks. Quantitative kinematic analysis is all about the numbers. Biomedical engineers measure, compute, and compare numerical data that describe motion. This might include calculating how far a joint moves, how fast a limb accelerates, or how long a foot stays in contact with the ground. The goal is to objectively determine how different factors, like muscle composition or footwear, affect movement. This data-driven approach is essential for advancing our understanding of biomechanics. Analyzing human movement, several factors can influence kinematic variables. These include muscle fiber composition, footwear fatigue, injury history, and the running surface. Each of these elements can change how a person moves, affecting stride length, knee angle, or ground contact time. Biomedical engineers consider all these factors to get a complete picture of movement and to make recommendations for performance or injury prevention. Observation-based methods are a key part of qualitative kinematic analysis. Biomedical engineers watch how a person moves, looking for patterns or irregularities. This might involve slow-motion video or live observation during athletic performance. By carefully observing movement, engineers can identify issues that might not be obvious from numbers alone, such as subtle changes in posture or timing. Video-based analysis allows for detailed examination of movement. By recording an athlete or patient, biomedical engineers can replay and analyze the footage frame by frame. This helps in identifying specific moments where movement patterns change or where inefficiencies occur. Video analysis is especially useful for comparing before and after scenarios, such as pre- and post-injury movement. Textual methods involve considering the environment and circumstances surrounding movement. For example, running on grass versus concrete can lead to different kinematic patterns. Biomedical engineers take into account these contextual factors to ensure their analysis is relevant and accurate. This holistic approach helps in making better recommendations for training or rehabilitation. Qualitative analysis in biomechanics follows a systematic approach. First, the movement is observed, either live or via video. Next, the movement is broken down into phases such as takeoff, flight, and landing in a jump. Each phase is analyzed for key characteristics like joint angles or timing. Finally, the findings are interpreted to identify strengths, weaknesses, or potential injury risks. To analyze movement effectively, it's important to break it down into distinct phases. For example, in running, we might look at the stance phase, swing phase, and flight phase. Each phase has its own characteristics and challenges. By focusing on one phase at a time, biomedical engineers can pinpoint where improvements can be made or where problems might arise. In kinematic analysis, certain variables are especially important. These include stride length, knee angle, and ground contact time. By measuring and analyzing these variables, biomedical engineers can assess performance and identify areas for improvement. Each variable provides unique insights into how the body moves and responds to different conditions. Textual analysis means looking beyond the numbers to understand the full picture. For example, an athlete's performance might change depending on the weather, the type of shoes they wear, or their fatigue level. By considering these factors, biomedical engineers can make more accurate assessments and recommendations. This approach ensures that analysis is both practical and relevant. Let's look at a practical example of qualitative analysis. Suppose a runner is experiencing knee pain. By observing their running form, a biomedical engineer might notice that their knee collapses inward during each stride. This observation can lead to recommendations for strengthening exercises or changes in running technique, helping to prevent injury and improve performance. To improve qualitative analysis, biomedical engineers should use a systematic approach. This includes careful observation, breaking movement into phases, and considering contextual factors. By following these steps, engineers can provide more accurate and useful feedback, leading to better outcomes for athletes and patients alike. Best practices for qualitative analysis include using multiple observation methods, involving experts from different fields, and regularly updating analysis techniques. By staying current with new research and technology, biomedical engineers can ensure their analyses are as effective as possible. Collaboration and continuous learning are key to success in this field. Quantitative analysis in biomechanics involves collecting and analyzing numerical data. This might include using motion capture systems, force plates, or wearable sensors to measure how the body moves. The data collected is then used to calculate variables like velocity, acceleration, and joint angles. This approach provides objective, repeatable results that can be used to track progress or compare different techniques. Perform quantitative analysis. Biomedical engineers use a variety of tools to collect motion data. Motion capture systems track the movement of markers placed on the body, while force plates measure the forces exerted during movement. Wearable sensors can provide real-time feedback on joint angles and acceleration. Together, these tools provide a detailed picture of how the body moves. Once data is collected, it's time to analyze the numbers. Biomedical engineers use software to calculate key variables such as velocity, acceleration, and joint angles. These calculations help identify patterns and trends, making it easier to compare different movements or track changes over time. The results can be used to improve performance, prevent injuries, or guide rehabilitation. Comparing data sets is a crucial part of quantitative analysis. By looking at how variables change under different conditions, such as before and after an intervention, biomedical engineers can assess the effectiveness of treatments or training programs. This objective approach ensures that recommendations are based on solid evidence, not just intuition. Let's consider an example of quantitative analysis. Suppose we want to know how a new type of running shoe affects stride length. By collecting motion data from runners wearing both the old and new shoes, we can calculate and compare stride lengths. If the new shoes lead to a longer stride, we have objective evidence to support their effectiveness. Interpreting the results of quantitative analysis requires both technical skill and practical knowledge. Biomedical engineers must understand what the numbers mean in the context of human movement. This might involve comparing results to established norms, looking for significant changes, or identifying outliers. The goal is to turn raw data into actionable insights. After analysis, it's important to report findings clearly and accurately. Biomedical engineers often present their results in reports, presentations, or consultations. Visual aids like graphs and charts can help make complex data more understandable. Clear communication ensures that recommendations are followed and that everyone involved understands the implications of the analysis. The ultimate goal of kinematic analysis is to improve human movement. Whether it's enhancing athletic performance, preventing injuries, or aiding rehabilitation, the insights gained from both qualitative and quantitative analysis can make a real difference. Biomedical engineers work closely with athletes, coaches, and healthcare professionals to implement changes based on their findings. Kinematic analysis is not without its challenges. Collecting accurate data can be difficult, especially in real-world settings. Variability between individuals, environmental factors, and equipment limitations can all affect the results. Biomedical engineers must be aware of these challenges and take steps to minimize their impact, ensuring that their analyses are as reliable as possible. The field of biomechanics is constantly evolving. Advances in technology such as improved motion capture systems and wearable sensors are making it easier to collect and analyze data. As our understanding of human movement grows, so too does our ability to enhance performance and prevent injuries. The future of kinematic analysis is bright, with new tools and techniques on the horizon. Let's recap the key concepts from this chapter. Kinematics is the study of motion, focusing on how things move rather than why. Both qualitative and quantitative analyses are essential for understanding human movement. By considering factors like muscle composition, footwear, and environment, biomedical engineers can provide valuable insights and recommendations. Kinematic analysis has many applications in sports. Coaches use it to refine technique, prevent injuries, and enhance performance. By analyzing movement patterns, they can tailor training programs to individual athletes. This scientific approach is transforming the way we think about sports and athletic development. Rehabilitation. Kinematic analysis helps track progress and guide treatment. By measuring how a patient moves before and after an intervention, healthcare professionals can assess the effectiveness of therapy. This objective feedback is invaluable for designing personalized rehabilitation programs and ensuring the best possible outcomes. Wrap up. Linear kinematics provides a powerful framework for understanding human movement. By combining qualitative and quantitative analyses, biomedical engineers can uncover the secrets of motion and help people move better, safer, and more efficiently. Whether in sports, rehabilitation, or everyday life, the principles of kinematics are making a real difference. Thanks for joining us on this journey through the science of movement.